Welcome to the next session on Module 5. In this session, we will be dealing with the instrumental methods of analysis. Instrumental methods, they have several advantages over volumetric analysis because in instrumental methods, results will be more accurate as it doesn't have any manual errors. Reactions which doesn't make use of indicators, they can be carried out using instrumentation methods. Then only very less amount of sample is required, as well as strong acids, strong bases, colored solutions, precipitated solutions all can be analyzed using instrumental methods. And even if the elements are present in trace quantities also, it can be analyzed easily and accurately using instrumental methods. So in this module, we will be dealing with 5 instrumental techniques. That is colorimetry, conductometry, potentiometry, atomic absorption spectroscopy, and flame photometry. Now, what do you mean by chemical analysis? Chemical analysis means it involves identification, determination, and finding the amount and molecular structure of a substance. Now, chemical analysis, it is of two types, qualitative analysis and quantitative analysis. Qualitative analysis involves identification of a compound or compounds in a mixture. It is called qualitative analysis, whereas quantitative analysis means the determination of the amount of element or substance present in a sample. That means we will be determining the quantity of a element or substance present in a sample. That is called quantitative analysis. Now let us see the instrumental method, colorimetry. So this method, it is used for solutions which are colored or which can give color with a suitable reagent. And the color intensity, it is directly proportional to the concentration of the solution. That means if the solution is more concentrated, then the color will be more. Color of the solution will be more. Now, colorimetry, it is based on Beer-Lambert's law. Beer's law states that amount of light absorbed by a solution is proportional to concentration of the solution. That means if the concentration of the solution is high, amount of light absorbed will be high. That means the absorbance will be high. So absorbance, it is directly proportional to concentration according to Beer's law. Whereas Lambert's law states that amount of light absorbed by a solution is proportional to path length of the medium. See, this is the sample cell or the cuvette in which we take the sample solution. So path length means it is this distance. That is the distance through which the light passes through the medium. This is called the path length. Okay, since we are using the same sample cell for measuring the absorbance of different solutions, this path length, it remains the same because we are making use of the same cuvette or same sample cell. Therefore, path length or T, it remains the same. So, as per Lambert's law, absorbance, it is directly proportional to the path length. That means path length, it is indicated by the letter T. So, according to Beer's law, absorbance is directly proportional to concentration, whereas according to Lambert's law, absorbance is directly proportional to the path length or the thickness of the medium, that is represented as T. So, absorbance, it becomes directly proportional to C and T. That means by removing the proportionality sign, absorbance is equal to a constant. This constant, it is called the molar absorption coefficient, that into C into T. So this is called Beer-Lambert's law. Absorbance is equal to epsilon, that is molar absorption coefficient into concentration of the solution into path length. And if the path length is also constant, means we can say absorbance, it is directly related to concentration. It becomes directly proportional to concentration. That means as concentration of the solution increases, absorbance also increases. For the colorimetric estimation of copper, it is that copper ions, they will react with ammonia to form a deep blue colored complex called the cupra ammonium complex. This complex, it is having an intense blue color. So if the concentration of the copper ions increases, means intensity of color also increases. Therefore, absorbance also increases. Now, instrumental technique, that is instrumentation. What are the parts of a colorimeter? See, colorimeter, it has a light source. Tungsten lamp, it acts as a light source. From the light source, light passes through a slit. And through the slit, again it passes through the lens. And after passing through the lens, it passes through a filter. This filter, it will filter or allow to pass only light of specific wavelength through it. So here, for the colorimetric estimation of copper, we will adjust the knob of the colorimeter to 620 nanometers. Because the visible range of spectrum, it is from 400 to 700 nanometers. So we will set the absorbance at 620 nanometers so that the blue color, it will give maximum absorbance in that region. Therefore, we are setting the absorbance at 620 nanometers. Or the wavelength at 620 nanometers. So this filter, it will allow only specific wavelength. So in this case, it will be allowing only light of wavelength 620 nanometers to pass through it. Now this light, it will pass through this sample solution. Okay, and from the sample solution, the amount of light absorbed, it will be directly recorded. So the output will show you the absorbance or the amount of light that is absorbed by the sample solution. So the instrument, it has the parts, that is light source, which is a tungsten lamp, then filter, which provides only desired wavelength to pass through it, then the sample cell and the photocell detector. Now procedure, it is the monochromatic light, that means light of specific wavelength, it is allowed to fall on the sample cell. So first we will prepare a blank solution. It will be taken in the sample cell and placed in the path of the light beam. Then its absorbance will be adjusted to 0. Now the analyte solutions will be placed in the path of the light and absorbance is measured. Finally, a graph is plotted with absorbance along the y-axis and the volume or the concentration of the analyte taken along the x-axis, from which we will be able to determine the concentration of the unknown solution of the analyte that is given to you. So that is the procedure. Now for the colorimetric estimation of copper, the solutions required are copper sulfate solution and ammonia solution. So these solutions will be provided to you and we have to prepare these solutions, that is, these solutions, they are prepared in 50 ml volumetric flask. So 50 ml standard flask you have to take. To first standard flask, you will be adding 2 ml copper sulfate plus 5 ml of ammonia, and then it will be made up to 100 ml using distilled water. To the second flask, you will be adding 4 ml of copper sulfate, 5 ml of ammonia and distilled water. Third one, you will be adding 6 ml of copper sulfate, 5 ml of ammonia and distilled water, and you will add distilled water, make up to the mark. Now in the next standard flask, 8 ml of copper sulfate along with 5 ml ammonia and distilled water. Then to the next standard flask, 10 ml of copper sulfate, 5 ml of ammonia and distilled water. So here as you move, you can see here it was only 2 ml copper sulfate, here it is 4, here it is 6, here 8 and here 10. So as the amount of copper sulfate increases, the intensity of color also, blue color also increases. Now test solution means it is unknown volume of copper sulfate. You will be provided with an unknown volume of copper sulfate. In all these you know the volume of copper sulfate, whereas in test solution you don't know the volume of copper sulfate. Some volume it has been given to you. To that you have to add 5 ml of ammonia and you have to make it up to the mark using distilled water. Now blank solution means it will not contain the analyte sample. Here the analyte sample, it is copper sulfate. So blank solution, it is prepared without copper sulfate. It will have only 5 ml of ammonia and distilled water. Now all these samples, all these made up samples, they are shaken thoroughly so that they all have a uniform concentration. Now the solutions are ready. Now next step is each of these solutions. First we'll take blank. Blank solution, it will be taken in the cuvette or the sample cell, and you will transfer the blank solution into the sample cell, and then you place it in the colorimeter. Then you switch on the absorbance, and if the absorbance is not 0, you will adjust the knob so that the absorbance, it is set to 0. Now you will discard the blank solution, and then you will take the standard solutions which you have prepared using 2 ml copper sulfate, 4 ml, 6 ml, 8 ml and 10 ml copper sulfate solutions. One by one you will be taking, and you will be noting down the readings. Then finally you will take the test solution. That volume also you will note it down. Now with these values you will be plotting a graph with absorbance along the y-axis and volume of copper sulfate along the x-axis. You will be getting a calibration curve, which is a straight line graph passing through the origin. Here if it passes through the origin means Beer-Lambert's law is followed. That is, because when the volume of copper sulfate here, it will be 0. When the volume of copper sulfate is 0, absorbance is 0, because absorbance, it is directly related to the concentration of copper sulfate according to Beer-Lambert's law. So absorbance, it is 0 when the concentration of copper sulfate is 0. So you will be getting a calibration curve passing through the origin. See here, now in this we are getting, for the test solution you are getting 0.15. So you will be plotting here absorbance. So 0.15, it corresponds to the test solution. You just extrapolate the graph where it touches the calibration curve. From there downward you extrapolate. This will give you the volume of copper sulfate that is present in the test solution. So now the volume of copper sulfate in the test solution, it is known to you. So you can calculate the amount of copper that is present, that is 249.54 gram of copper sulfate. This is the molecular mass of copper sulfate pentahydrate. Okay, this much gram of copper sulfate, it will have 63.54 gram of copper, that is the atomic mass of copper. So this much copper, the weight of this copper sulfate pentahydrate is 249.54. In that, how much gram of copper is present? 63.54. So given 8 gram of copper sulfate, this 8 gram, it is the weight of copper sulfate which we have used for preparing the stock solution, 1000 ml of stock solution, because copper sulfate solution, it was initially given to you to prepare the standard solutions. So those standard solutions, that stock solution which was given to you for preparing the standard solution, it was made by dissolving 8 gram of copper sulfate in 1000 ml of water. So 8 gram of copper sulfate, it will contain this divided by molecular mass into 8. That is, this much gram of copper, it is present in the stock solution. So 1000 ml of stock solution, it contains 2.03 gram of copper. From the graph you are getting V test, that is volume of the test solution. So volume of test solution into 2.03 divided by 1000 will give you the amount of copper that is present in the test sample. So thus you are able to determine the amount of copper in a given sample of copper sulfate. Okay, thank you.